Hi, my name is Tom Hoeffel, and I'm a chemistry teacher, and this channel is all about trying to teach students chemistry. In this video, we're going to be talking about the energy changes in a Bohr model. So I have an example of a Bohr model here with its different rings, and they're labeled n equals 1, n equals 2, n equals 3, n equals 4, because the n is the principal quantum number. And if we had an electron that was in a low energy orbital, or orbit, I should say, like the n equals 1 level, and if I wanted to get into one of these higher orbitals, I would actually have to supply energy to the atom to promote that electron into an excited state. Now, that electron typically doesn't want to stay in that excited state, so it's going to jump back down into its ground state, or a lower energy orbital, and in that process, it's going to release a photon, and that's how it releases its energy. It's going to be the energy of a photon, and that photon is going to have a specific energy, frequency, and wavelength. And that's the type of problem that we're going to talk about today. So we're going to pretend we have an electron that's in the excited state. It's in the n equals 3 ring, and we're going to see what happens when that electron jumps back down into a more stable state at the n equals 2 ring. Now, in order to do this, we kind of have to know, well, what energy does it start with, and what type of energy will it end up with? And this is where we have the Rydberg's equation. So this is the Rydberg's constant, which is equal to negative 2.178 times 10 to the negative 18 joules, and that's all divided by n squared. Now remember, n is the ring that you're on, and also our principal quantum number. So if we're starting at n equals 3, let's figure out what would the energy be on the n equals 3 ring. So we're going to plug in our calculator, negative 2.178 times 10 to the negative 18 joules, and we're going to divide it by 3 squared, because we're talking about the energy on the third level. When we do that, we get this number of negative 2.42 times 10 to the negative 19 joules. And then we're just going to repeat that process for the n equals 2 ring. What is the energy when it's at the 2 level? So I take this negative 2.178 times 10 to the negative 18, and this time I'm going to divide by 2 squared. And when I get that, I get negative 5.445 times 10 to the negative 19 joules. So this is where I'm starting, and this is where I'm ending up. And whenever we do a change in energy, or delta E, it's always going to be the energy final minus the energy initial. Okay? Well, the final, where we're finally going to end up, is at the 2 level. So we want to put in the energy level of 2 minus where we started. We started at the n equals 3 ring, so it would be the energy at the 3rd level. And then I just plug these numbers in. So the energy level at 2, we figured out to be negative 5.445 times 10 to the negative 19 joules. And we're going to subtract that from the energy level at 3, which is negative 2.42 times 10 to the negative 19 joules. And when I do the subtraction there, I get this number of negative 3.025 times 10 to the negative 19 joules. Okay? And this is the amount of energy that's going to be released when it goes from the n equals 3 to the n equals 2. So there's really no such thing as kind of like negative energy. This negative sign right here is just telling us that energy is being emitted. So it's more of a direction than anything else. Okay? So we get this photon that will come in packets of 3.025 times 10 to the negative 19 every time we get this electron to jump from n equals 3 to n equals 2. Now, this photon that has this specific energy is going to have a particular frequency and wavelength as well. So to figure out the frequency, we're going to use this equation. Now, the energy input that we put in, we're not going to carry this negative sign because it's not negative energy. It's this energy, and then the negative sign means that the energy is being emitted, okay? So we're going to plug in this energy right here, 3.025 times 10 to the negative 19, okay? And then what we're going to do is we're going to divide that by Planck's constant in order to get the frequency, okay? So it's the energy divided by Planck's constant. So the energy, 3.025 times 10 to the negative 19 joules, divided by Planck's constant, which is 6.626 times 10 to the negative 34 joule seconds. You will see that the joules cancel out, and I'm going to have seconds in the denominator. Now, if seconds is in the denominator, we call that a per second, which is the appropriate value for a frequency. If I do the math here, this ends up being 4.57 times 10 to the positive 14 seconds to the negative 1, or what we call a per second. So here's the energy, and here's the frequency of that photon. Now, with the frequency, we then can use the speed of light equation to figure out the wavelength of this particular photon. We're going to do that by dividing by frequency on both sides. So wavelength is equal to the speed of light divided by the frequency. The speed of light being 2.998, times 10 to the 8th power meters per second, divided by our frequency of 4.57 times 10 to the 14th per seconds. And as you can see, the per seconds are going to cancel out, and I'm going to be left with the wavelength of 6.57 times 10 to the negative 7 meters. And if I were to convert that, that would be 657 nanometers for my wavelength, okay? And just let you know, that falls into the visible spectrum of the electromagnetic spectrum, and that's going to be orange light. So we would get an orange band from this electron that's jumping from 3 to 2 because it has this specific energy as an energy packet of its photon, and that energy has a corresponding frequency of 4.57 times 10 to the 14th per second, and that frequency then has a corresponding wavelength, okay? So when we have these jumps of electrons, either down or up, there's always a corresponding energy, frequency, and wavelength. And a lot of chemistry teachers want to make sure that you understand that relationship between the energy change and how that has a corresponding frequency and a corresponding wavelength. So I hope this small problem or this small example helps you understand the energy changes in a Bohr model and how we're treating that electron like a wave because of its frequency and wavelength. And if this has helped you, okay, please like and subscribe. It helps YouTube algorithm get this information out to other students that might be struggling in chemistry.